I'm waiting for YouTube. I can't see anything. My computer is so slow. Okay. Oh my gosh. Okay, can you, let me see. I think we're almost there. Let me do one thing. You all are so patient. I feel like an idiot. Okay, let's see. Are we in business? You tell me. If not, if the camera's frozen, I'll just get rid of it. Can you hear me at least? Okay, thank God. Okay, let's do this. Let me get my questions because I had to just restart everything. My computer's a minimum of 10 years old, probably more. You would think I would invest in a new one. Okay, so yesterday, just to refresh you two real quick, what we were doing those factoring problems, right? And I've kind of got everything kind of all shaded in. But basically said we were looking at things that were separated by pluses and minuses. We were looking at variables to sort of variable compositions that we were the same. And then we said we factored out the smallest exponent, and we tried to put, stuff back inside the parentheses that was the correct stuff, was sort of the gist of what we were doing. So let me jump down here to 44, and I'm copying stuff down. Give me 1 second. If there are comments, I will certainly address them, but I'm not looking at them just yet. So 2x squared. I hope everybody's having a good day. Man, I was like, okay, I've been so goofy with the setting up the stream. Today I'm going to do it correctly. And I thought I had it, and of course, I did not. So I think I'm going to blame it on my old computer because it was acting pretty wonky. So make sure I copy everything down here correctly. Sorry, I write like a little kid. I've kind of written it pretty large. So notice we do have two terms here. So let me hop back over there. Okay, so we're doing okay. So I guess let me go ahead and do this one. So we've got basically one, and it looks like there's a big lag between what I'm saying and what I'm seeing on my screen. So communication may be a little slow here, back and forth. So unfortunately, I think what I'm going to do is just start talking. Maybe text, definitely send messages in the chat. I'm keeping an eye on it. I think that's going to be probably the easiest way to talk. Okay, so let's do this. So we've got 2x squared. Hey, Queen Bee, and it's good to see you. 2x squared. We've got an x minus 1 to the third power. X plus 3 to a power. We've got 2x squared plus 3 to a power. And I'm even going to sort of let me change that. So when I look at it, I look at my constant. Whoops. I look at my constant. And then again, I look at the variable. So I see an x to a power. And then just like I said, we've got an x minus 1 to a power, an x plus 3 to a power, a 2x squared plus 3 to a power. And then I see this big plus sign. So that's separating one term from the other. And yes, that first term is pretty big, but it's got a lot of stuff that's being multiplied together. That's just fine. And the same thing with the second one. Now again, I'm kind of looking at it individually. I'm thinking, okay, let me look at the numerical part. So there's a 10. So I'm comparing the 2 and the 10. I'm thinking, well, I could factor something out there. And then I notice, well, there's an x originally. There's also an x in this term. And again, we've got an x minus 1 and an x minus 1. Those are in common, x plus 3, 2x squared plus 3, and 2x squared plus 3. So all of those things, whichever ones are in common, we can factor them out. And it's not like everything has to match up just like it did in my example here. So sorry, I'm trying to really quickly get this to where I can see the stream a little better on my channel because I'm just viewing it through OBS for the moment, the streaming software. Okay, so the first thing I'm going to do is, again, I just look at the numerical part. I think I've got a 2 and a 10. You know, what could I factor out from 2 and 10? Well, I think what I could factor out would be a 2, so that takes care of that part. And then I think, well, I've got an x to a power, and I've got an x to a power. So again, I can factor out, did I say something else? Okay, maybe coefficient. Oh yeah, sorry about the other video. That was my problem. I shouldn't have tried to have fun. So no more dance party, I guess. So we've got an x in common and an x in common. So I'm going to factor out the x. And again, I'm going to factor out the smaller exponent. So I've got a 2 and a 3. I'm going to pull out a 2. And we just keep repeating this process. So I've got an x minus 1 here, and I've got an x minus 1 here. Again, I'm recognizing that these are being broke up by that plus sign in between. So I can factor out an x minus 1. It looks like the smallest exponent is a 3. We've got an x plus 3 and an x plus 3. Same thing, I could factor out an x plus 3. The smallest power, it looks like, is 4. And then we've got 2x squared plus 3, 2x squared plus 3, so we could factor out a 2x squared plus 3. Oh, in this case, the powers are the same, so we can factor that exponent of 5 out. Okay, so that is the factoring. That's how I sort of just go through it. I'm just thinking what matches, and then from what matches in terms of the variables or what's inside the parentheses, just pull out the smallest power. That's visually all I'm looking at. If there had been another term in here, so again, we're not done with this yet. I'm sorry. So we're not done. I'm off on a tangent. If there had been another term in here, things would have to match in all 1, 2, 3 terms. So do be careful about that. Okay, so let's go back. Let's keep working on this one. So this is just what I factored out, right? This is just the factored out stuff. And now what I want to think is, what would go back inside of the parentheses or the brackets so that when I multiply things out, everything works. So again, I've got way too big of handwriting. So what I'm going to do here, let me see if I can't make this a little smaller. So again, that stuff that we have here, that's what is factored out. And I think you should still be able to see that. So let me try to write a little bit smaller here. Okay, so this is all, again, I'm going to have stuff inside of it. I'm going to use brackets, use parentheses, whatever. And then I'm going to have a plus sign. So there's my original plus sign that was separating those two terms. And now again, I just sort of think, what do I need to multiply by so that if I distribute, I get the original stuff back? So I'm thinking 2 multiplied by what is 2? Well, that would just be times 1. And I'm not going to write the times 1. So I'm thinking x squared times what is going to give me the x squared. I'm looking at the first term. I'm trying to get the first term back, so that's why I'm just looking at this portion so far. Again, x squared times 1 is x squared, so I don't need anything there. Let's see. I've got an x minus 1 to the third power. Again, we had an x minus 1 to the third power, so I don't need anything there. We pulled out an x plus 3 to the fourth power, but I need to get an x plus 3 to the fifth power when I distribute. So in that case, it looks like we're going to need yet another x plus 3. And the idea is that when I distribute out this x plus 3 to the fourth, it's going to multiply by that x plus 3 to the first. And, well, that's going to give me that x plus 3 to the fifth back. So that's the idea, right? The exponents are going to add up to a 5, and that's what we want. So let's clean this up a little bit. And now the same thing, I think, well, 2x squared plus 3 raised to the 5th. Well, if I just multiply that by 1, I'm going to get 2x squared plus 3 to the 5th, just like I want. So it looks like that's the only term that's missing, in fact. So I'm going to erase all of this and make it a little bit closer here. So that's the first part, and now I just play the same game. So now I'm focused in on this second term, and I'm thinking if I multiply this by something, I have to get that stuff back, is what I'm doing. And please type something in the chat or the comments just to know that I know everyone's alive. Tell me where you're from, if nothing else. That's always interests me. But that's what I'm doing in this question. And of course, pay attention to. Okay, so 2 times, it looks like 2 times 5 is going to give me that 10. And I'm just using random colors. I hope it's not distracting. Let me make that a 5. And then I'm thinking, well, x squared times what is going to be x to the 3rd power? Well, there I think I would just need an x to the 1st power. I've got x plus 3 raised to the 4th power. I want to get an x plus 3 raised to the 4th power, so I could just multiply by 1. So I don't need anything extra there. And again, last but not least, we said 2x squared plus 3 raised to the 5th. Well, again, if you multiply that by 1, that's going to give me 2x squared plus 3 raised to the 5th. So it looks like the, once I factor all that stuff out, in this case, it looks like what we're left with inside the brackets is quite simple. So I'm going to do one last step, which is just combine like terms. So this is 2x squared. And again, please let me know if you think I made a mistake. These are so easy just to miss a sign or exponent or copy something down wrong. By all means, it's certainly easy. And then inside the brackets, I've got an x and a 5x. That's going to be 6x plus 3. If you really wanted to, Chicago, nice. We went to Chicago 2 or 3 years ago. I forget where we were. It was for a math conference. But it was nice. I liked it. I used to live about 5 hours from Chicago. So anyways, sorry, that's why I shouldn't ask. So notice in the 6x plus 3, we could actually factor out a 2. And in that case, we could have this as 2 times, it looks like 3x. No, we can't. We can factor out a 3. Oh my gosh, I'm losing my mind. We can factor out a 3. I can hear you all screaming. Factor out a 3. So if we factor out a 3, oh my goodness. If we factor out a 3, I'll need a 2x and a plus 1. So again, I could replace that 6x plus 3 with all of this stuff. But this 3, I can multiply by this 2. So I could really write all of this as 6x squared multiplied by x minus 1 to the 3rd, x plus 3 to the 4th, 2x squared plus 3 to the 5th. We again accounted for that 3 because we multiplied by the 2 out front, and then we've got a 2x plus 1 left over. Holy moly. That is now, how do we get 6x? Did I mess up? So when I was left with the stuff inside the brackets, so at this step, I'm just combining that x and that 5x to produce the 6x inside the brackets, is all I'm doing. And then I'm just leaving the plus 3 over next to it. So that's how we get what's inside the brackets here. And then I'm not writing the whole next line down, the part that's in blue. I'm just saying, okay, 6x plus 3, we could rewrite that as 3 times 2x plus 1. And if you take that 3 that's out front, multiply it by the 2, you get that 6, and then you just basically write everything else down, is what I'm trying to say. If that makes sense. Let me know if that makes sense. So I had 5x multiplied by x minus 1. I'm trying to think how you would get that. So somebody maybe out there can verify. Did I mess up? I think did I leave something out? I did, no, yes. I did leave something out. You are absolutely correct. Oh my goodness. See, this is why I said check it. Okay, so 5x. We left out an x minus 1, didn't we? That's exactly, yes, you are exactly correct. Thank you so much. I see what I did wrong. So, okay. Queen bee, you're saving my life here. And I was even saying it, right? It's so easy to make a little mistake here, just like I did. Okay, so let's go back over the little mistake that I did. Little, but very important, right? I mean, I totally botched it. So we said we factored out an x minus 1 to the third, but we need an x minus 1 to the fourth. So we also need that x minus 1, just like Queen Bee is saying. Yes, I did not account for the x minus 1. 100%. So now let me stick those back in brackets. And then, okay. But now back to the same idea, right? Let's clean up what's inside. So it looks like we're going to get a 5x squared when we multiply, and that's going to be my highest power inside of the brackets. So I'm going to go ahead and just write that first. And then I'm going to get a negative 5x. Negative 5x plus x is going to be negative 4x. And then it looks like we're going to have this plus 3 left over. So Queen Bee, does that look correct to you? I'm going to defer to you now. So tell me if that's what you got. 5x squared minus 5x plus x, that's negative 4x. I think that looks okay. And that stuff in the middle, you can mess with it, b squared. That shouldn't, I was going to say, that shouldn't factor any further. So that looks to me now perfect. Okay. Excellent. Okay, thank you so much. Any questions on that one? If not, I'm going to move on. We'll start talking about domain. There's a lot of domain questions, and those are questions that I've noticed. It doesn't matter if it's Calc 1, Calc 2, Calc 3. People always have issues with domain, so we'll talk about that a little bit. So a quick question, too. Why are you watching this? Like, do you just want an algebra review? Are you going into calculus? Are you going to teach a friend or a child? You know, I'm just curious. And if you don't want to share, you certainly don't have to. And I don't mean that directly to Queen Bee because we have been chatting. Just to anyone that feels like answering it. I'm just kind of curious. Okay, let's jump on to the next ones. And again, I'm probably going to stop at 6 o'clock tonight. And tomorrow I can't do. Thursday maybe, Friday maybe, Saturday I should be able to do at some point, and then Sunday as well. So just stay tuned, I guess. So we want to find the domain. Now, the domain you really need to know. You need to know the domains of lots of different functions. And if you've only seen Algebra 1, you may not have seen all of this. If you've seen, more than that, you should have certainly discussed it. And everything that I'm going to talk about here, I mean, you'll certainly see questions like this in calculus. Find the domain of this, blah blah blah, and certainly all the ones that are on this worksheet would absolutely be fair game. Fair game. Trig review. We will do that trig review. Phaser, just for you because you've been here and I appreciate it. Oh, cool. You're just here for fun. That's nice. Also for fun. I will do a trig review just for you. We'll do it. I think some other people would like it too. Struggle Bus. You're funny. I like your name. So, okay. So let's talk about the domain. And I guess I'll just hit them one by one as we go through it. So 45 f of x, f of x equals x squared plus 3x plus 4. So again, this type of function has a special name. When you have x's to whole power, whole numbers, positive whole numbers, or to the 0 power, which is going to be x to the 0 or 1, and then you're just left with a constant. So if you have something of this form separated by pluses or minuses, notice you don't want like an x in the denominator of a fraction, but we don't have that here. other than SOHCAHTOA. SOHCAHTOA is useful. That's you can do a whole lot with SOHCAHTOA. So if you know SOHCAHTOA, you're halfway there, Queen Bee. So okay. So for this one, okay, yes, it's got a special name. We call it quadratic, and I think probably if you've had any algebra or above, anything relatively recently, I would assume a lot, a fair number of you know what it is. If you don't know the graph of this and you don't look at that function and say, oh, yes, Patrick, that's a quadratic that opens upwards because the coefficient in front of x squared is a +1. You should absolutely 100% know that in a calculus course. You should be able to complete the square on it. You should be able to put it in a vertex form. You should be able to find the vertex. You should be able to, what else do we want to do with this? With more, you should be able to set it equal to 0 and solve. All of that stuff. This is known as a quadratic, but more generally, if you have something that looks like, so you've got f of x, it basically says you have x to some power. And again, the idea is n is, we would say, a non-negative integer. So 0, 1, 2, 3, 4, etc. So eventually it says there's a highest power, that highest power of n. And then, okay, I should have put a little space in there. Because I could be multiplying that by some number. I'll call it a sub n generically. And then I've got some other ones in there as well. And notice the constants, some of them can be 0. And eventually you get down to, let me use an a here as well. We'll say, oh, I should have done this a better way. Oh my goodness. Let's make this, sorry, let me make these match up. I'm totally being sloppy with my notation. A sub n minus 1, a sub 1 times x plus a sub 0. This is more generally known as a polynomial, is the important thing. Now, there's some important properties about polynomials that you want to know. Yes, Queen Bee, the degree is 2. Absolutely correct. And that's useful to know because the degree, it says you can have a maximum that number of solutions. So if I were to set this equal to 0 and try to solve it, that degree tells me the maximum number of solutions I could have. So I could have at most 2. If you go into complex numbers, you can actually show that you have exactly 2. But under real numbers, you can have at most 2. The same thing, if it was to the 10th power, you could have at most 10 real solutions. And polynomials are nice in mathematics. So those of you that go on to take more math, hey there, long number. Okay, oh no, did you, no, you should, okay, is there a different pattern? I was looking for the pattern in your name there. Yeah, there's a lot of other things you can use too to get information. Descartes' rule of signs. You can look at if you look at the number of solutions when you set it equal to 0. For example, if it's a repeated root or not, you can tell about what the graph does based on that. Based on the degree, you can tell about the end behavior, whether it goes to positive infinity or negative infinity on the left side and the right side. There's a whole lot of information you can get from a polynomial just by looking at it. And again, you got to know all this stuff and classify it. Yes, one way we can find solutions is we use the rational root theorem. Absolutely. That was something, yes, yeah, for sure, that's important. You can do that with polynomials. That is something absolutely useful to know. So Calculus 1, 2, 3 is throwing in some extra things as well about that you can do with polynomials that are useful. So, okay. The thing that you should know about a polynomial in general, so I'm not drawing this quadratic, I'm drawing a generic polynomial. So I'm going to draw a generic polynomial, is they're smooth. And they have little twists and turns. They could be a straight line if they want to be. But they always have, they're just kind of smooth, they're continuous, like there's no break. There's not going to be a break in the graph. That doesn't happen with a polynomial. So when there's no break in the graph, like on my little purple generic polynomial that I've sketched here, well, we say that is known as a continuous function if there's no breaks. And knowing that a function is continuous ends up being a very useful property in math because it's like you know that values don't get skipped over, for example. Nothing kind of weird happens. So that ends up being useful. Okay. The moral of the story of this is, what is the domain? What is the domain of this function? That's what we're trying to ask ourselves. And what does it mean even to be in the domain, right? Maybe we should have even addressed this first. So to be in the domain, the way I think about it, so to be in the domain, x can't produce something bad. Okay, well, that's nice. So x, what is x? X is any number. Pick your favorite number. 2, 3, 4, 1,000,005, pi, e to the 0.1, whatever. Pick your favorite number. That's what x is. So to be in the domain, that number, when we throw it into our function, it can't produce something bad. The two bad things for you that you'll usually be looking for is you don't want to plug it into the denominator, do some arithmetic, and get 0. You don't want that. Okay? So it's bad if you get 0 in the denominator of a fraction. That value of x will be thrown out of the domain. We won't use it. Everything else is good, just that. The other thing that's going to be bad is after you do all the arithmetic underneath, say, a square root, you don't want a negative number. You don't want a negative number. So minus number, let me write, you don't want a negative number. Those are going to be typically the restrictions on the domain in an algebra course, pre-calculus, trig. This is what you're going to see. And I've got a square root here, but really more generically, it's any even powered root, to the 4th power, to the 6th power, to the 8th power, etc. So I'm going to write it's bad. I'm going to write a generic n here, and I'm going to say n is an even, non-negative. We don't want 0. That doesn't make it. We'll just say it is an even positive integer. That's all we need. Yeah. It's an even positive integer. Sorry, it's been a long day for your friend Patrick here. I had a nice job interview. That was good. I needed that. So we'll see where it goes. Wish me luck. Okay. So what if it's an but notice if it's an odd root, we're fine because we can take cube roots of negative numbers. Okay. So the moral of the story again is you can say one of two things. I could look at this function and I could say it's a polynomial. In particular, it's a quadratic. Therefore, its domain is all real numbers. I could just say the domain is from negative infinity to positive infinity because it is a polynomial. If you gave that that reasoning on a quiz or a test, your math instructor would say, yes, that is exactly correct. The other reason, again, is too, I mean, think about if you plug in a value of x. You know, if I plug it in here, I'll square it. Okay. Well, that doesn't give me 0 in the denominator of a fraction, and that doesn't give me a negative number under a square root, so I can't really mess up this x squared part. Well, I can take 3 times any number, right? There's nothing that when I evaluate 3 times a number is going to give me something undefined. So again, there's no value of x that would mess that part up. Well, then you just add 4 at the end. What's the problem? Well, that's the point. There is no problem with any value of x. That's why the domain is all real numbers. So that's kind of the reasoning. That's how I think about domain. I mean, that's what it is. So let's look at another one here. Let's go through ones. So 46 is a really good example of what I just said, which I'm sure is why I picked this a long time ago. So here we have f of x equals 2x minus 1. So, you know, and now what value of x or value, what values of x are bad, if any, right? Because there doesn't have to be. Like in my previous example, they were all good. So I'm thinking, could I fill in a value for x so that when I do the arithmetic at the bottom, I either get 0 in the denominator of a fraction because I don't want that, that's bad, or somehow I end up getting a negative number underneath an even-powered root. Well, there's not even any square roots or fourth roots or sixth roots floating around in this one, so I think we're pretty safe on this second part. But I think it's pretty clear, right? Yeah, exactly. So, I mean, what is bad? Well, I think if I ever see an x in the denominator of a fraction, I take whatever is down there and I set it equal to 0. And I think, is there anything that will produce 0 in that denominator after I do the arithmetic? If so, kick it out. If not, okay, you don't have to worry about it. So yeah, exactly. So it's bad if x minus 1 equals 0, right? That's the bad value of x. Well, that's easy. We just add 1 to both sides and we get x equals 1. So just like Phaser says, hey, x equals 1 again, don't forget, x equals 1 is bad. So we want all numbers except x equals 1. So again, if we do that on a number line, typically you'll write this in interval notation. So here's negative infinity, here's positive infinity. So we would say the domain is from negative infinity up to 1, parentheses, because we don't include it, union, parentheses from 1 to infinity. And yeah, and the way Phaser has it is also perfect. That is set notation. Typically, at least in I don't know if you're all from the States, and in USA, every book I've seen, you do see set notation, some for sure, especially when you get into higher math. But I think you'll typically see interval notation, which is why you'll see me use it. So, okay, let's keep going. So that one was pretty easy, right? I just say, hey, what messes up the bottom? That's all I care about. So 47, I look at this one, 2x plus 3. Now, we said it's bad to find a value of x that makes the denominator 0. Is it bad, to have a value of x that makes the numerator 0? Is it bad to have 0 on the top? I mean, is that bad? Is that undefined? Is 0 over 4 undefined? Well, no, definitely not. 0 divided by 4 is 0. That's why it's no problem to have 0 in the numerator. But 4 divided by 0, what's 4 divided by 0? It's not 0. It's not 1. It's not infinity, right? It's not any of those. It's undefined. Okay, so again, that's just why we don't want 0 in the denominator. So for this one, so now I'm just looking at the numerator individually. I'm thinking, is there any value of x that would produce 0 underneath the square root, 0, a negative number underneath the square root? I'm already thinking of the next part. A negative number underneath the square root or an even-powered root? Or is there a number of x that would produce 0 in the denominator of that numerator? Well, no, again, this is a polynomial, right? This is just a line if you graph it, y equals 2x plus 3. Are the ranges as important to find as the domains? That is a very important question, and I will answer that in 1 minute. Bring me back if I zone out, but I won't. That's a good one. So in this case, the numerator is a line, so there's no problem with it. So all I really need to look at, all I care about, all I'm looking at, all eyes are just on the denominator. And again, I'm thinking, if I take the denominator and I set it equal to 0, does it have any solutions? Well, I think for this one, we could either add 1. So we could do this in 2 different ways, just to remind you. We could add 1, and then we can take the square root of both sides. But don't forget, when we take the square root, we need to include a positive and a negative on one of those sides. And well, the square root of -1 is just 1. So that gives us our two solutions, x equals 1, x equals -1. Now the other totally fine way to do this is to factor. This is a difference of perfect squares. And again, you could distribute this out. This is one of those a teacher would say, you should definitely know that one. And I would agree. Again, if you're taking a calculus course, if you're not, if you're new to it, maybe not. But it's certainly going to be super duper extremely common. Something like x squared minus 1, x squared minus 4, and it's not like it has to be a whole number. X squared minus 2, that's still factors. We just get not whole numbers. Well, again, we know how to solve these. We set each one equal to 0. This will give us x equals 1, and this will give us x equals -1. So, apples and apples. So my domain in this case, again, if you want to see it on a number line, we just found the bad values, right? We figured out what makes the denominator equal to 0. We said it's -1 and +1, which means everything else is good that I'm shading in, roughly. So again, the domain would just be from -infinity up to -1. We skip over -1 and go up to +1. We have to skip over +1. And then we just keep on trucking to infinity. So variables in the bottom, set them equal to 0. So let me ask you just a little variation on this one. So this is always the fun of a live stream. So we had 2x plus 3 in the numerator before. We had x squared minus 1 before. What if I make this a +1? So notice this is a new question. So what is the domain of that one, right? So, and again, I hate this lag between when I'm talking and while they're answering or thinking about it. So yeah, so for this one, what would the domain be? And I'm still thinking of the numerator, 2x plus 3, there was no problems before, there's no problems now. X squared plus 1. Okay, so you're saying the solution to that would be imaginary numbers. And when it comes to imaginary numbers, that's fine. We don't even kick them out. So typically in these courses, let's restrict ourselves, restrict to real numbers. So there's definitely stuff you can do when you start talking about imaginary numbers and complex numbers. I definitely agree with that. But for now, if we restrict ourselves just to just thinking about real numbers, is there any value of x that would, before we had values, we had values of x that would make the denominator 0. Is there any value of x that makes the denominator 0? Yeah, exactly. So the domain will never, you said the domain will never be 0, but what you meant is, I know what you meant. You meant to say the denominator will never be 0. So yeah, so I think, well, if I set this equal to 0, I'm going to do the same thing. I'm really thinking, that's why I'm putting the question mark, does this equation have solutions? If it has solutions using real numbers, I throw them away. If it doesn't have solutions, well then I didn't find anything bad, which means so far everything's good. That's kind of the logic. So if I try to factor this, you can try to factor it, it doesn't work. Yeah, Phaser, totally understand. And you saw me mess up earlier, so we're all good here. Everybody's friends. And yeah, just like Queen Bee is saying, she's pointing out, if you tried to use this square root method, we would subtract the -1. We would take the square root of both sides. But the square root of -1 is an imaginary number. It's I. Well, that's not a real number. So the square root of -1, this is not a real number. And again, real has a very technical mathy meaning, right? It is not a real number. Which means it's not a decimal or a whole number or a negative number or any of those things. Didn't say anything about complex numbers, okay? It's not a real number. And what that means is this has no solutions, that equation. So to me that says ain't, there ain't nothing bad, right? Everything's good. All the x's are good. So in that case, nothing messed up the top. Nothing makes the denominator 0. So hey, it's all real numbers. I would still go through this process though. I mean, so for example, for me, x squared plus 1, I would say, oh, that's a sum of perfect squares. It doesn't factor, so there's no solutions. Boom. But if it was something more complicated, I would think, well, let me set it equal to 0 and see what happens. And I said I would forget, but I managed to not. Phaser asked a good question about ranges. So what about the range, and is it important? What about the range, and is it important? Let's start with the second question first, and I would say absolutely. So it's absolutely important. We would like to know the range for sure. Right? And intuitively, and I know you're thinking it, right? Like, okay, it's nice to know what values you can start with, but it's nice to know what's going to happen at the end, right? Maybe you go in and invest your money, right? I'm no longer a spring chicken. I go invest my money, and the financial person says, hey, if you make a minimum of this return, maybe 3% per year, versus you make this high-end return, which is 15%. I want to know, if I take my money today, what's the range of money I'll have down the road, right? If I only end up with between $50 and $100, well, that ain't any good. But if I end up between $1 million and $5 million, I'm starting to think, okay, But I want to know that range, what happens. So, yeah, absolutely. So yes, we want to know the range. So let's find it, right? Let's find it. But notice we never seem to, right? We never seem to. And why? Because it turns out to be it's just a harder question to answer. There's just more involved in finding the domain. So when it comes to finding the domain, to me, I honestly can't think of an exception to these two rules in a calculus score. I mean, there's really nothing. If there's an x in the denominator of a fraction, set it equal to 0. See if there's something that messes it up. If there's even-powered roots, make sure you don't get negative numbers under them. So how do we find the range? You could find the inverse, and then you switch the x and the y. But if it was easy to do that, it would be easy to find the range in the first place. So that is a clever solution. Switch x to y and then do the same procedure, right? But that's the wrinkle. Because it's not always easy to find an inverse, right? Really easily, to switch those x's and y's and solve for them. I mean, what if I gave you y equals e to the x times the square root of x minus sine of x? So I know we're not doing trig just yet, but it is on that worksheet, plus, x minus 4 over tangent of x, right? Replace the x's with y's, and now I'll give you a lot of money if you can, if you can solve. So that's the problem. So in general, though, there's not a generic procedure. So there's just not a general procedure. A very useful thing to do. The best thing I know, So the best thing I know to help find the range, guess what it is? Guess what the best thing to find the range that I know of? And don't say a calculator. That's a good answer. Or a computer, What do you think would be the best way? What do you think would be a useful tool to finding the range? I wish you could just say a calculator. Suppose you got to program the calculator. Okay, yeah, oh, no, calculator graph, you're cheating again. I agree if you had one. I agree, but like, how does the calculator know what to graph? They could be brute forcing it. I don't think that's what they do, though. In fact, I know it's not. So it's kind of a question you may not know because you're not there yet, and the answer is, hey, guess what? La-ti-da, calculus. That is the best way that if somebody gave me a question in general, unless it was a real basic function, like a line or something I could reason out, if somebody said, for example, this really wonky one right here, what is the range of that? I would start using calculus, and it would turn into a hot mess. But like there's a procedure to start doing things. So that's the answer. But in general, there's not a good way algebraically to find the range. And that is a very good question, which is why I took a couple minutes talking about it, because people don't talk about it, and it's a useful. Okay, so let's keep going. 48, I think we've got about 10 minutes. And then, so maybe we can go through these a little quicker. So f of x equals the square root of x plus 4. So kind of the first question, I think, is, okay, so I'm recognizing there's a root of some sort in there, right? I'm recognizing there's a root. And I'm asking myself, is it an even-powered root? Is it an even-powered root? And recall that when we write a square root, we don't write it. We don't write the value. Let me try that one more time. We don't write the number. Sorry, that looks a little wonky, but it's understood there's a 2 right there. So this is an even-powered root. It's the square root. So it is an even-powered root. The exponent is 1/2. You are correct. We could write this as x plus 4 to the 1/2. That is absolutely true. Is there a difference between a function and a linear equation? Yes, absolutely. And I will come back to that one in 1 second as well. Absolutely. The short answer is a linear equation is a very specific type of function. A function doesn't have to be a linear equation at all, is your short answer. It's like a girl is a human, but a human doesn't have to be a girl. Right? So is the analogy, my first little analogy. So yes, the exponent is to the 1/2. So and this is something also important, you need to be able to convert from fractional exponents, like to that 1/2 power I had a second ago, to roots, and vice versa. So if you don't remember that, let me jot it down. I was going to say look it up, but I'm not going to. So if we have x, say, to the n over m power, we can write that as the m root of x raised to the power of n. So that's how you switch from a fraction exponent to radical or root notation. So in this case, the answer is yes. So this is an even-powered root. So I should say, if yes, we'll do this next thing. And then we'll say if no. If no, it's nice because you just don't worry about it. Okay? Don't worry about it. I say don't worry about it as long as there's nothing about x that will make 0 in the denominator. Okay, so you still have to think about that, but otherwise, don't worry about it. If yes, take what's under and solve that stuff. I'm using English here. We want that to be greater than or equal to 0 because we can take the square root of 0 and we can take the square root of any positive number. So in this case, what I'm thinking, so a second ago we were kind of finding what was bad, right? When I was finding what made the denominator equal to 0, I took my equation I found what was equal to 0. I got those values. Okay, that one didn't have a solution. But a second ago, when they had a solution, we said those were bad. Now what I'm simply going to do is I'm going to look at what's underneath the even-powered root. I want to produce values at the end of the day that are 0 or larger. So I just have to solve x plus 4 greater than or equal to 0. And again, in this case, notice these are the good values. So again, what I found previously, we kicked out of the domain. What I'm finding now are the values we're going to keep. We're going to throw everything else out. So do make that distinction, because I've noticed when I've taught this in courses before, sometimes people glaze over that or don't catch it. Well, this is again so now I'm back to all of those inequalities we did, right? A couple days ago or yesterday or whenever we were doing them, both those days, I think. Depending on the inequality you have, you do different things to solve it. Well, fortunately, this is just a linear inequality. We can just subtract 4. So it says x needs to be greater than or equal to -4. So there's -4. Everything larger is good. So in this case, we would just say the domain is from -4 to infinity. And that would be it. Okay, so yeah, just like Phaser has, there is the domain. That would be correct. Let me do a little variation on this. So 45 star. Suppose my function. Oh, and let me ask the. Yeah. So Queen Bee. So let me know if my answer just worked for you, about there being a difference between a function and a linear equation. So like a parabola, x squared plus, we'll just say x squared plus 1. This is a function. This is a function. But when you graph it, right, it's not a line. It's going to be a parabola. So this is not a linear. This is not a linear function. So I don't know if you mean, is there a difference between a linear function and a linear equation? Yes, in that sense, a function, we're just kind of given a formula. We're saying, hey, look at this formula and think about the graph of it. Whereas for an equation, you're actually setting it equal to some value and trying to get a value for x at the end. I hope that makes sense. I hope that answers it. So suppose I do change it to this. Suppose I have exactly what I had a second ago, but now instead of having the square root of x plus 4 in the numerator, I chuck it in the denominator. Okay, you're so nice. If it's just me and you, Queen Bee, we can have a little one-on-one session. You just tell me. Okay, and maybe I'll wrap it up with this one here. So if I just change it to 1 over the square root of x plus 4, would it make sense to solve x plus 4? We said, oh, I need the stuff underneath the inequality to be greater than or equal to 0. Is this correct? Would it make sense to now solve that inequality to find the domain? Right, because now I'm getting 0 under the square root, and that's fine, because 0 times 0 is 0. So is it okay to solve the exact same thing? And then we would produce the exact same domain, right? We would say it's -4 to infinity. So is that correct, I would say? So calculus says yes. Keep doing the same thing. Change of heart. So we'll go with 1 no and 1 yes. All right, Queen Bee, you're going to be the, I think it's you three. You're going to be the, yeah, exactly, right? We just want it to be greater than 0, right? Because the problem is, right, if we get x plus 4, if we think about the equal part, right, if we make the denominator, if we make the stuff underneath the square root equal to 0, the square root of 0 is 0, we're going to get 0 down here now, which is, right, that's bad. So now I wouldn't be able to do that. So now, you know, up here, it's okay to get 0 underneath the square root. No problem. That's no problem. Here, though, we can't, though, because it's living in the basement. So this is not correct. All we have to do is make one little modification. And that one little modification, right, is we just keep it strictly greater than 0. That way we don't produce exactly. We don't need 0 in the denominator. Not only do we not need it, we don't want it. So absolutely. Yeah, and then so if I kick it out, okay, I'll solve it. We do the same thing, subtract 4. Notice again the inequality only flips if you multiply or divide by a negative number. So adding or subtracting, whatever, doesn't change it. So my domain is going to be x just strictly greater than -4. So, okay, it's almost going to be the same thing, except now we'll just leave -4 out. So that's what I'm saying. When you go through these, like, you can't totally turn your brain off, right? You still got to think about it a little bit. Say, oh, it's in the denominator. I can't just say greater than or equal to 0 because 0 is bad. So you just modify it a little bit. So that's what I'm saying, You want to be as robotic as you can about them, but not too much. So I will let you think about 48. Notice 48 is a combination. I've got two 48s on here. Oh my gosh. I didn't notice that on my sheet. So there's two 48s on the second 48. Notice you've got restrictions from the square root in the numerator. And you also need to see if there's anything that'll make the denominator 0. And there should be. If you don't remember, do you all remember what the domain of ln of x is? So kind of a little jump ahead on some of the other domain questions. Recall that a logarithm function, sorry, my graph is really cruddy here. A generic logarithm will go through 1, 0. So this is log base b of x. If that base is greater than 1, which is typically what you'll see. Notice this has a domain of, so this one has a domain of 0 to infinity. It's almost like the domain of a square root, but you can get 0 inside of a square root. That's fine. You can't get 0 inside of a logarithm. So we just use larger than 0. So for 48, we didn't need to find the bad stuff in the denominator. For the second 48, yes, you will. You'll have to find two restrictions. You're going to have to find what makes the numerator happy, in the sense that you want you're going to find the good values of x. So then you're going to have a little chunk of values that are good. And then you're going to look at the denominator, and you should get some values that are bad. And you have to think, are any of those bad values inside of that good chunk that you found from the first part? Because if those bad values are inside of that good chunk, well, that good chunk is now restricted even more, right? You've got to throw those values away too. So then you've got that good chunk minus 2 points from the denominator. So that is the idea. So you're going to get restrictions from the numerator. You're going to get restrictions from the denominator in that question. You should. The second 48. And then you just have to keep what's left. Okay. So another way to think about it, what's bad for the numerator and what's bad for the denominator, just kick all of those out, and whatever you have left is going to be the domain. So in general, if you have a domain question, if you have the ln, I wrote ln, if you have some logarithm, so to find, if you don't remember these, so to find the domain, if you have some logarithm and you have some stuff, and by some stuff, I mean it could be some big complicated formula, it could be something simple, it could be whatever, it could be lots of things. What you have to solve, you take whatever that some stuff is, whatever that formula is that's sitting next to the logarithm, and you have to make it strictly greater than 0. And to solve this, how to solve some stuff, well, again, right, the answer is it depends. We saw all of those inequalities that we solved previously, which was the point of doing all those inequalities previously, because it ties into all these domain questions. That's really where we were going with all of those inequalities. Okay, good luck, Phaser. I'm hopping off here. Hope to see you again. It's a pleasure. I do enjoy having some feedback, so you really make it better for me. good luck with life, and I hope to see you in a few days. So I think I'm going to bail too, my friends. So yeah, so we'll keep going. So if you do try to work on these, that's really all you're doing on the next ones. And again, so like 49, you could take the stuff in the parentheses, x minus 3. That has to be greater than 0. Boom, there's your inequality. In 50, I would think x squared minus 1, that has to be greater than 0. How do I solve that quadratic inequality? Well, we talked about those. And then I would think what makes the denominator bad. Okay. And then, yeah, that's how I would do those. Last but not least, it looks like after that, we've got our graph transformation. So I think we could probably knock these out in one more session. And then we'll see what happens, and we can keep, maybe we can jump onto trig. We'll see how it goes. All right, my friends, have a good evening, and yeah, I hope life treats you well. I hope you have a good few days. Stay strong, stay healthy, and yeah, I'll see you soon. All right, my friends, take care.